Yeah, good afternoon, student. Good afternoon. So, am I visible and audible? Just let me know in the chat box if I'm audible and visible. Yashu, can you give me a response? If you can hear me and if you are able to see me on my screen, just give me a simple reply in the chat box. Hello? Are you there? Yeah. Okay, okay. Thank you so much for your reply. So, let's start with the class today. So today we are going to see a new topic. Okay, so it is periodic table, and in this lesson we will discuss the classification of elements and the periodicity in properties. Okay, so first of all, why do we need to classify the elements? So what is the reason to classify the element? Why do we need to classify? So in case of in your kitchen, you might have seen kitchen utensils arranged in a racks, and for clothes we have a wardrobe, and for bathroom utilities we used to keep them in a separate containers, right? So why they have been arranged like this? Why we are arranging a particular set of thing in a particular rack? So to take out easily, right? So like that, totally we have 118 elements are known. So to study these elements easily, and also some new elements, they are also synthesized continuously, not only 118 elements. Scientists may also can discuss some other new elements also. So some new elements are also synthesized continuously. So to make the study of elements easy and efficient, we are classifying the elements in a respective column and in the respective rows. Okay. So many scientists have come up with their own classification by using their laws. Like Dauberner, he came with the law of triads, and Newland, he came with the law of octaves. So like this, many scientists, they have come. Mendeleev came up with the Mendeleev's periodic law. In between, Lothar Meyer, he scientist came and gave some ideas. So like this, many scientists have come taking their laws and things, theories, and elements were classified according to their laws. Okay. But in our syllabus, in our JEE and NEET syllabus, we don't have those classification part. Only the last classification is given to us in the syllabus. Okay. So that is in accordance with modern periodic law. That is in accordance with modern periodic law. So now let's start this lesson with the modern periodic table. Okay. So in this modern periodic table, so the first part of this talks about, and today we are going to see these topics, which is the introduction to modern periodic table and the periods and groups related informations of periodic table and the blocks in periodic table. Got it? So now let us move on to the introduction to modern periodic table. So let's start with this. Which, Hashira, good afternoon. Which slide you want? This slide? Good afternoon, students. Good afternoon to all the new joiners. Yeah, who are joining. Which slide you are asking? Is this slide you were talking about? Okay, okay. Have you noted it down? Yes? Okay. Okay, no issues. So let's start with the thing. So in this lesson, the first topic talks about these three. Yeah, and now coming to the introduction to modern periodic table. So this man is a scientist, okay? And his name is Henry Moseley. His name is Henry Moseley. So what he did, he observed some regularities in the characteristics of X-ray spectra of the elements. Okay, he took some elements and he studied the X-ray properties spectrum, okay, and the characteristics of those X-ray spectrum, and he observed one particular regularity. A regular interval was observed by him while doing this experiment. And from his experiment, he plotted a graph, okay, versus, I'll show you that. Yeah, he plotted a graph of square root of nu, that is frequency, square root of the frequency of that X-ray versus the atomic number, okay. And this graph gave a straight line. I'll show you. This graph gave a straight line like this. So Z is the atomic number and the square root of frequency is given in y-axis, and he observed a straight line. As the atomic number increases, the square root of that nu, that also increases. Okay, so he observed this. And from this experiment, he gave one law, and that law is called as modern periodic law. Okay, so the law states that the physical and chemical properties of the elements are the periodic functions of their atomic number. So whatever may be the property we take, as the atomic number increases, so they are going to follow some regularity in that particular property. Okay, so that only the physical and chemical property, both of elements, they are the periodic functions of their atomic number. So this is one of the very important modern periodic law, and the periodic table which we are using now, that is in accordance with this modern periodic law only. Okay. So any doubt from this? Shall we move on to the next slide? Yes. So you need to study the thing, the x-axis and y-axis part you have to study, and the observation. Observation is a straight line. Got it? Now let us move on to the next slide. In the modern periodic law, you have to keep in mind. Now coming to the atomic number. So what is an atomic number? Can anyone tell me what is an atomic number? What is an atomic number? One of you can define the atomic number. Definition. What is atomic number, my dear students? Now if you can try for it, right? You don't have to get scared of this class. Just open up your minds and tell something. Type something in the chat box. What is atomic number? None of you? Many of you are here. One of you can try, no? Okay. Okay, I'll go with this. The atomic number is the number of electrons in the neutral atom and or the number of protons in the atom. Okay, it is equal to the number of electrons in the neutral atom and or it is equal to the number of protons. Okay, and also it relates to the quantum number and the electronic configuration. Quantum number, and you might have studied about the 4 quantum numbers in structure of atom lesson. Principal quantum number, azimuthal quantum numbers, magnetic quantum number, and spin quantum number. So the atomic number is related to that quantum number and the electronic configuration also. So thus the periodic law is the consequence of periodic variation of electronic configuration. So in the upcoming slides, you will notice that periodic variation of electronic configuration, which is the consequence of this periodic law. Okay. Now coming to the long form of the periodic table. This modern periodic table is otherwise called as long form of the periodic table. Okay, the other name is long form. And in this periodic table, we have 7 periods which are called as horizontal rows and 18 groups in the system. Groups are always otherwise called as vertical columns. Got it? So how many periods we are having? 7 periods and 18 groups in the periodic table. In the modern periodic table, the period number corresponds to the principal quantum number. I told you, no, the 4 quantum number. So in that, the first quantum number is principal quantum number, and this is represented by the letter n. So that n represents the period number. N represents the period number. So in a similar way, the outer electronic configurations are placed in the same group. So similar outer electronic configuration containing elements are placed in a same vertical column and they corresponds to the group. So n denotes the number of the shell and the similar electronic configuration denotes the similar elements placed in a corresponding group. Got it? So this is a general introduction of the modern periodic table. Now we will see the modern periodic table now. I'll show you. So here is a modern periodic table, and here we have, yeah, and two more rows are also there. So totally we have 7 horizontal rows which are called as period, and you can see that. So it is 1, 2, 3, 4, 5, 6, and 7. Okay, and we have 18 groups here. One starting from 1, 2, 3 till 10, and here, sorry, 3 till 12, and 13 to 18. So 18 groups we are having. Okay, so the last two rows which you can see here, the last two rows, these elements are called as lanthanoids and actinoids. So this particular row, this series is called as lanthanoids, and this series is called as actinoids. Got it? So this is the periodic table, and here we have some groups and some blocks and other related information. So I will discuss with you in the next slides. Got it? So any doubts so far? Any doubts so far from the introduction part of this? Shall we move on to the next thing? Yes or no? Okay, I'll go with the next thing. The nomenclature of elements with atomic number, yeah, greater than 100. So in the periodic table, yeah, thank you so much, students, for your response. So in the periodic table, we have 118 elements, right? So in that, the elements which are having atomic number more than this 100, they have to follow some rule. So while naming that compound, we have to follow some rules to name that compound. So why we need to do that? So new elements with very high atomic number which are being discovered, they are found to be highly unstable in nature. All the new elements which we are finding out now, they are found to be very highly unstable in nature. So the synthesis of that element, highly unstable element, requires the sophisticated environment. Like we have to use some costly equipment and laboratories needed to synthesis those elements. Okay. Now for this element, why do we need to why do we need this nomenclature? Because if I'm taking this atomic number 104 element, so Americans only found this. So those Americans, they named it as Rutherfordium. Okay, Rutherford only discovered, so they named it as Rutherfordium. But Sovietists, they named it Kurchatovium. Okay, so different people, they came up with their ideas and they started to name on their own wish for a single element. So what IUPAC did, you all know what is IUPAC, right? International Union of Pure and Applied Chemistry. So that institution, so they recommended to use the systematic nomenclature until new elements discovery has been proved. So they gave some set of rules to name the newly discovered compounds. So that's why we are following those rules to name the compounds which are having atomic number more than 100. Okay. Now, what is the root? What is the rule? So an element name, it is equal to the roots for each digit in atomic number plus IUM. Okay. So you don't have to worry about it. I'll give you a table. So for 0 to 9, so only we have these 10 digits in the numbers, right? So if you're having 0 in your atomic number, you have to give the name nil. And for that nil, the abbreviation is CN. Okay. So the each name's first letter will be taken as abbreviation. And for 1, it is un. For 2, it is bi. 3 tri. 4 quad. 5 pent. 6 hex. 7 sept. 8 oct. And 9 yin. Okay. So this was the rule given by the IUPAC. So these are the notations for IUPAC nomenclature of elements. Okay. Now we will try to follow this notation and then we will try to name the compound now. So if the atomic number of an element is 112, so we have three numbers, 1, 1 and 2. So those are the roots. And for 1, what name we have to use? It is un. And for 1 again un, for 2 it is bi. So we have to name it like un, bi. In the suffix you have to use IUM. So IUM is used. So what is the name? Un and bium. Got it? And if I want to give the symbol for this element, I have to take that abbreviation U, U and B. So just connect it. That will be the symbol for that element. Got it? Want the previous slide? Okay. Yeah, take a note of it. Okay, okay, Ashu, take a note. No issues. Once you are done with it, just give me a message. I will go with the next slide. Shall we move on to the next thing? Yes? Okay. Okay. Yeah. Yeah. Okay. So now we will see one more example. Atomic number is 108. So what is the roots? 1, 0 and 8. And for 1, what we have to use? Un. And for 0, it is nil. And for 8, it is oct. Right? Un, nil, oct. Then what is the suffix? IUM is the suffix. So it is un, nil, oct, em. The name of the element is un, nil, octium. And take the abbreviation. It is U, N and O. Right? So the symbol will be U, N, O. Got it? So very easy. You just have to memorize the tabular column. That's it. Okay. For 9, it is ENN. Okay. It is not non-N like in case of organic chemistry. Here you have to use ENN for 9. Okay. Yeah. So now using this set of rules, scientists have discovered and gave the name for all the 18 elements which are above this 100 atomic number. So you can find the IUPAC nomenclature as well as IUPAC official name. For unknown name, it is Mendelium. And for the next element, Nobelium, Laurentium, Rutherfordium, Dubnium, Seaborgium, Bohrium, Hassium, Yttrium, Darmstadtium, Röntgenium, Copernicium, Nihonium, Flerovium, Moscovium, Livermorium, Tennessine, and Ogneson. Okay, so these are the official names and also the notation that we have used. That is given to you. So you should know both. Okay. So in the previous years in 2021 NEET and in some papers, so they asked question in that in the case of match the following type. Okay, they will give some 4 elements, their official name and the IUPAC nomenclature thing, and they asked us to find out the incorrect match, and they asked us to find out the correct match. Okay, so like that they have asked. So you should know both the columns. Okay, so both the columns are very important, including the symbol you study. Okay, so I think we can move on to the next topic. Shall I? Did you all take the screenshot of it? Yes. Okay. So yeah, the periods and groups in periodic table. So this is the second topic that we are going to see. So first, let me discuss about the periods in periodic table. Okay. So the filling of electrons into the different orbitals in a shell is called as electronic configuration. Filling of electrons into different orbitals in a shell is electronic configuration. Okay, we have 4 different orbitals, sp, df, and we are going to fill those electrons, and that is going to give us the electronic configuration. Just give me a moment. Yeah, sorry. Fine. So the periods indicates the number of the shells. The periods indicates the number of the shell. We have 7 periods and we have 7 shells. So first period is the filling of the lowest level K. So the first shell is the K shell. Okay, K shell contains 1s orbital. So we have hydrogen, that is 1s2, 1s1, and we have one more element in the first period, that is helium, and the electronic configuration is 1s2. So here the 1 represents the principal quantum number that I have told you, or the period number, or the shell number, first shell. Okay. So in the first period, totally we have 2 elements. Total elements in the first period is 2. Okay. Now coming to the second period. So the second period is the filling of L shell. So first K, then L. So in the L shell, we have lithium and beryllium first. And for lithium, the configuration is 1s2 and 2s1. And for beryllium, it is 1s2 and 2s2. And from boron till neon. So these elements belongs to one particular block. That's why it is given separately. So for these 6 elements, the electrons are getting filled in p orbital. Electrons are getting filled in p orbital. So filling of takes place. For boron, you can see the last electron is entering into the p orbital. So it is 1s2, 2s2 and 2p1. And like that for carbon, it is 1s2, 2s2, 2p2. For nitrogen, 2p3. For oxygen, 2p4. For fluorine, 2p5. And for neon, it is 2p6. Okay, 1s2, 2s2, 2p6. So how many elements we have total for this second period? Can anyone tell me the total number of elements present in the second period? What is the total elements? Total elements is equal to 8. Okay, totally we have 8. So 6 in the right hand side and 2 in the left hand side. Got it? Now coming to the third period is the filling of M shell. Filling of M shell leads to the third period elements. So coming to the S block, it is sodium and magnesium. Okay, whose atomic number is 11 and 12. And for sodium, S electron, S orbital is going to get filled. It is 3s1. Since it belongs to the third period, it is 3s1. And for magnesium, it is 3s2. Okay. And from aluminium till argon, here the filling of p orbital takes place. The configuration of aluminium is 3s2, 3p1, and the outer electronic configuration of argon is 3s2, 3p6. So from 1 till 6, the p orbital is getting filled. And in this period also, we have totally 8 elements. Got it? Shall I move on to the next slide? Yes. Do you have any doubt on the thing that we have discussed so far, students? If everything is clear, just type yes in the chat box, or if you're having any doubt, just ask me, I'll repeat it again. No, okay. So we will go with the next thing, fourth period. So the fourth period is, yeah, okay, students, okay. The fourth period is the filling of N shell. So L, M, and now N. Okay, here we have potassium and calcium. For potassium, the configuration is 4s1, and for calcium, it is 4s2. Okay, and also we have few more elements from scandium till zinc. Here, the filling of d orbital takes place, especially 3d orbital. For the fourth period elements, 3d orbitals will be filled. Okay, for scandium, it is 3d1, 4s2. It is 3d1, 4s2. And for zinc, it is 3d10, 4s2. Okay. So from scandium till zinc, we have 10 elements, right? So scandium 3d1 means titanium, it will be 3d2, 4s2. And for vanadium, it is 3d3. For chromium, 3d4, 5, 6, 7, 8, and 10. 9 and 10. Got it? So this is how the electrons are getting filled in the 3d orbitals for the fourth period elements from scandium till zinc. And these elements, these 10 elements are called as 3d transition series. They are also called as 3d transition series. Got it? So far what we have seen in the fourth period, first 2 and next 10 elements. And some more elements are also going to be there in the fourth period. So those are these 6 elements from gallium till krypton. Okay. So here the filling of 4p orbital takes place. P orbital. You see for gallium, 4s2, 4p1. The last electron is entering into 4p1. And for krypton, it will be 4p6. Got it? So totally, how many elements we have in this period? First 2, next 10, last 6. So 2 plus 10 plus 6 is 18. Total elements will be 18. Okay, 18 elements are placed in the fourth period. where the filling of N shell takes place. Got it? So now let us move on to the fifth period. Yeah, in the fifth period, filling of O shell takes place. So here we have rubidium and strontium. For rubidium, it is 5s1, and for strontium, it is 5s2. Not only this, we have some more elements like we had in the fourth period. And here, yeah, these are those 10 elements from yttrium to cadmium. Okay, here filling of 4d orbital. In the previous case, we 3d orbitals got filled. No, so here it is 4d orbital. So from 4d1 5s2 till 4d10 5s2 it ends. And these elements are called as 4d transition series. Got it? And some more 6 elements filling of with the filling of 5p orbitals also takes place. So here it starts from indium 5s2 5p1 and it ends up with xenon 5s2 5p6. Okay, yeah. So totally how many elements we have in this particular period? So can anyone find the answer? How many elements totally? Yeah. Same as that of previous case, no? So 2 plus n plus 6, 18 elements. Totally, we have 18 elements in the fifth period also. Now coming to the sixth period. So here we have these elements. So first two is success. Filling of success takes place. And from atomic number 57 till 71, here the filling up of fourth electron orbital takes place. Okay, filling up of 4f orbital takes place here. And from hafnium till mercury, it is 5d. Filling of 5d takes place. And from thallium till this radon, it is 4p. Filling of 6p takes place. Sorry, filling up of previous slide. Yeah, yeah. Shall we move on to the next thing? Shall we move on to the next slide for the sixth period? Students? Okay, okay, dear. So if you need some more time also, let me know. Okay, fine, fine. Yeah, let's go with the next thing, sixth period. Yeah, it consists of 6s, 4f, 5d, and 6p. So totally, how many elements this particular sixth period contains? It contains 32 elements. It contains 32. You might be thinking where the 32 elements are located here. Only very few elements are seen on the screen. Where does this remaining elements come from? They come from the 4f part. Okay. So we have 57 till 71, right? So it consists of elements from cerium to lutetium, and in that part we have 14 elements, and those 14 elements are called as lanthanoid series from cerium to lutetium. So those 14 elements are called as lanthanoid series. So totally we have 32 elements in sixth period. Now coming to the last period of periodic table, that is the seventh period. Seventh period elements are also visible to you on the screen. So where the 7s orbital and then 5f, then 6d and 7p orbitals are going to be filled there. And some man-made radioactive elements are also there in this period. Okay, not only very few, all the elements present in this period are man-made radioactive elements only. And coming to this 5f, like in case of 4f, we have elements from actinium to lawrencium. So from actinium to lawrencium, we have 14 elements, and these 14 elements together are called as actinoid series. I have showed some two rows were there in the periodic table at the bottom, right? Lanthanoid and actinoid. So those are these 4f and 5f electrons. Got it? So is this periods topic clear to all of you? Do you have any doubt in the periods topic in the periodic table? Shall we go on with the groups? Any doubt from the period, students? So how many periods we have? 7 periods we have. In the first period, we have 2 elements. And the second period and third period, we have 8 elements. Then fourth and fifth period consist of 18 elements. And the last sixth and seventh period consist of 32 elements. Okay. So 2, 8, 8, 18, 18 and 32, 32. Got it? Fine. Now let us go on with the groups in the periodic table. So elements in a same group has similar configuration. Because of the similar configuration, the number of electrons present in that particular system will be same. So they exhibit similar properties. They exhibit similar physical property and they exhibit similar chemical property. So for example, I'll take this lithium group. The first group I have to. Atomic number of lithium is 3, sodium is 11, potassium it is 19, for rubidium it is 37, cesium 55, francium 87. So this is the atomic number of these elements. And this is the symbol. So which you can see there in that boxes itself. Okay. So these are the symbols. And the electronic configuration of this each element is, for lithium it is 1s2 2s1. Or we can represent that configuration as helium 2s1. So what does this helium denotes? It denotes the configuration, this configuration, 1s2. The configuration of helium is 1s2, right? So in place of this 1s2 in lithium, we are putting helium. Got it? Then coming to sodium, we have 11 electrons in sodium. So we are filling it in according to Aufbauer's principle, that is 1s2, 2s2, 2p6 and 3s1. Totally 11 electrons. Now this is the configuration of neon. Atomic number of neon is 10. Okay. So if the atomic number is 10, for neon, we have to write 1s2, 2s2 and 2p6. So in this place, we are putting neon. And the last thing alone is represented here, 3s1. And for potassium, same way, argon with 4s1. Then for rubidium, krypton gas with 5s1. And for cesium, xenon with 6s1. Such a very long, lengthy configuration it is. So I have given only the abbreviated part, that is xenon with 6s1 and for radon with 7s1. Got it? So in all these cases, you can observe that the outer electronic configuration is similar. 2s1, 3s1, 4s1, 5s1, 6s1 and 7s1. So generally, if I want to write, it is ns1, where n denotes the principal quantum number or the number of the shell. Okay. So since they are having the similar outer electronic configuration, they exhibit similar properties. That's all. Got it? So this is about the group. Now, yeah, okay, I'll repeat. So I have taken the first group for you as an example. Okay, this is these elements belongs to first group. And for all this first group elements, we can find the outer electronic configuration as same. And for lithium, it is 2s1. For sodium, you can see it is 3s1. And potassium, it is ending up with 4s1. So in the case, same way for rubidium, 5s1, cesium, 6s1, and francium, 7s1. Okay. So the general outer electronic configuration for this first period is first group is ns1, where n represents the principal quantum number or the number of the shell. If an element belongs to the first period, it is 1s1. And here lithium belongs to the second period. So that's why it is ending up with 2s1. And sodium belongs to third period. So that's why it is ending up with 3s1. So this n denotes the number of the period or the number of the shell or the principal quantum number. So what I have did, I have given the general outer electronic configuration to define this first group elements, and that is ns1. Okay, so since they are having the similar electronic configuration, they will behave in a similar manner. Their reactions will be similar. They can donate only one electron, which is there in that s orbital. So all the elements from this first group, they can donate only one electron. So all will form only 1 plus ion, Li plus, Na plus, K plus. So only that type of unipositive ions can be observed for this first group elements. So all the behaviors, all the physical and chemical behaviors, that is properties, they are similar since they are having the similar electronic configuration. Got it now? Shall I move on with the question for you? Yeah, I'll give a question. Is this clear for the student who have asked me to repeat again? Is this clear now? I don't know who have asked this question. Okay. Yeah. How would you justify the presence of 18 elements in the fifth period of the periodic table? Can anyone answer for this? How would you justify? How do you give the justification for the presence of, yeah, it is Nargis. Okay, Nargis. Good. Very good. Fine. Now you guys try to answer for this question. How would you justify the presence of 18 elements in the fifth period of the periodic table? I told, right? Each element contains each period contains specific elements. So how do we justify? In case of fifth period, we have 4d, 5s, 5p orbitals filled. And the order in which the energy of the available orbital is 5s lesser than 4d lesser than 5p. Means 5p is having the highest energy. So total number of orbitals will be 9 for this. Why? We have one s orbital, and how many d orbitals we have? We have 5 boxes, no? 5 d orbitals we have, and coming to p orbital, we have 3 p orbital, px, py, and pz. So totally how many orbital? 1, and here 5, and here 3. So totally it will be 9. Total number of orbital is 9, and each orbital can take 2 electrons, right? So the maximum number of electrons that can be accommodated in these 9 orbitals will be 18. Each orbital is taking 2, so 9 into 2 is 18. Okay, so 18 electrons it can accommodate. So that's why we have 18 elements in the fifth period. Got it? So whatever might be the s orbital, it can be 1s or 2s or 3s. S orbital is only 1. We have only one s orbital. And p orbital, 2p, 3p, 4p. To take any of the p orbital, only 3 are there. And for d, we have 5 orbital. Yeah, Hashira. Good, good, good. And for f, we have 7. Exactly correct. Great. Very good. Fine. So we have discussed the periods and the groups. Now we will move on to the blocks in the periodic table. Okay. Let us discuss the classification of S, P, D, and F block element. So first moving on to the S block. So S block consists of group number 1 and 2. So group number 1 and 2 belongs to S block. And group number 13 till 18, they belong to P block, but there is an exception. I told you, right? While I was teaching P block elements lesson, I told you there is an exception, and it is helium. Helium is an exception. It is not a P block element, but it is. You want the previous slide? Yeah. Okay. I'll show you. Shall I move on to the blocks? Did you all take down the thing? Yes. Okay. Yeah. Yes. Okay. Yeah. In P block, we have an exception, and that is helium. Helium is actually not a P block element. Last electron enters into S block, but since it is behaving like a 18th group element, which are noble gases, we are placing that helium there. And coming to D block consists of group 3 till 12. Okay, 3 till 12, and hydrogen is also kept above that. Okay, there is no position for hydrogen now in the modern periodic table. That's why it is placed separately. And coming to the last two, that is lanthanoids and actinoids, they are called as F block. So totally we have 4 blocks. So why this particular letter is given for each block? Because the last electron enters into that particular orbital. Suppose in case of lithium, lithium is called as an S block element because the last electron enters into the S orbital. 1s2 2s1, right? So likewise, the other elements are also getting the corresponding blocks. Got it? So this is about the thing. Coming to this hydrogen, as I've already told you, there is no such block for hydrogen. It is placed in the middle of the periodic table because it resembles both the S block, the first group, as well as the 17th group element. Hydrogen resembles the first group element's properties as well as the 17th group element property. So that's why it is not placed in either of those two groups and it is placed separately in the periodic table. Got it? Now I will discuss each and every block with you with some more information. First, I will start with S block. I want to talk about S block. Yeah, it is group number 1 and 2. So group 1 elements are called as alkali metals. As I have already told you, the general electronic configuration for this first group is NS1. And electronic configuration for the first group elements are NS1. So they easily, who are those they? Lithium, sodium, potassium, rubidium, cesium and francium, they lose their one electron which is there in NS1 orbital easily to form the +1 ion. They lose that one electron to form +1 ion. So lithium will lose and it will be converted to lithium plus, sodium will be converted to Na plus, potassium plus, rubidium plus, cesium plus, and francium. Francium is radioactive, so we will not study the chemistry of francium and radium, so we can leave that. So coming to the group 2, they are called as alkaline earth metals. General electronic configuration for alkaline earth metals is NS2. So in the NS orbital, it has 2 electrons. So they lose 2 electrons to form di-positive ion. They form di-positive ion. Like in case of beryllium, Be2 plus, magnesium 2 plus, calcium 2 plus, strontium 2 plus, barium 2 plus, and radium is radioactive. So we can leave that. Got it? So these are the general outer electronic configuration in which the corresponding element can lose its electron, outermost electron. Now coming to the next point, except lithium and beryllium, all other elements which are there in first group and second group, they form ionic compound. Okay, all other elements of the corresponding group forms ionic compound. Lithium and beryllium, they form only covalent compound. So these two elements, they form only covalent compounds. Covalent compounds are formed by the sharing of electrons and ionic compounds are formed by the transfer of electrons. Okay, so lithium and beryllium will share its electron whereas the other elements will transfer its electron. And talking about the metallic nature, it increases from top to bottom. On moving down the group, metallic character increases. Okay. Now, when you compare lithium and francium, which is more metallic? Francium is more metallic. Lithium is least metallic. Got it? So, when the metallic nature increases, reactivity of the elements also increases. Reactivity of the elements also increases. Now, francium and radium, they are highly reactive in nature. Okay. And that's why they are never found pure in nature. They always try to form the compound with the other element. If they are finding any element in the atmosphere, they will go and interact with them and they will try to form the compound. That's why we cannot separate the francium and radium. They are never exist in the pure form of it. Got it? So when metallic nature increases, reactivity also increases for those elements. And that's why the highly reactive elements are not found pure in the nature. Got it? So this is about the S block. And coming to P block. So P block consists of group 13 till 18. General electronic configuration of P block is NS2, NP1 to 6. Both S block and P block, they together are called as main group elements. If you combine both S block as well as P block, they together are called as main group elements. And this oxygen, if you see oxygen group, the 16th group, no, the oxygen group. So there is one special name for that 16th group, that is chalcogens. The special name for 16th group is chalcogens, and for 17th group it is halogens, fluorine, chlorine, bromine, iodine, astatine and tennessine. So these elements are called as halogens, and the 18th group is also having a special name, which are called as noble gases. Okay, and the electronic configuration for noble gases ns2np6. So the p orbital is completely filled. We have only 3 p orbitals, right? So in all the orbital, we have 2 electrons. So all the p orbital is completely filled. So these noble gases, it will never lose or it will never try to gain electrons. So very, very difficult to lose or gain the electrons for noble gases. So what, they never react. They don't have the tendency to lose its electron or gain electron. No, only if an element lose or gain an electron, we can tell that this particular element is reacting with the other. So since these noble gases are not having that ability, they are least reactive in nature. The reactivity for noble gases is very, very low. Okay. So all the points given in the slides are very important. Now one more thing I'll tell you. Metallic nature, as I already told you, when you go from top to bottom on moving down the group, metallic nature increases and the non-metallic character increases across the period. On moving down the group, metallic character increases. Across the period, non-metallic character increases. So now who is more non-metallic in nature? Group 17 and group 18. From 16 onwards, 16, 17, they have more non-metallic character. Got it? So they easily gain the electron. They easily gain the electron and they attain the nearest noble gas configuration easily. Got it? And become stable. This is about the P block elements. And tomorrow in the next class, we can discuss the D block and F block. And then we can jump to the remaining part, okay? Periodicity part. So today, we have seen the general introduction part of the periodic table and some information related to groups, periods, and the blocks, and the detailed explanation about the S block and P block. Got it? So yeah, I hope this session is very clear and useful to all of you. If you're having any doubts, you can ask. Otherwise, we can meet in the next class. Okay. Thank you so much, students, for listening to today's lecture. If you're having any doubt, you can let me know. No doubt. Okay. Bye-bye. Thank you. Thank you.